As Alessandro said, I will be talking for about 40 minutes. I hope you find it interesting. If you have any questions, please feel free to put into the chat thread, and we will have a Q&A session at the end. So with that, I will share my presentation, and I hope you enjoy it. Okay, it's just, there you go. Can you see that, Alessandro?
Yes, all good to go, John.
Perfect, excellent, thank you very much. Okay, so the subject for today's talk is the frequency domain and how it can be used to aid artificial intelligence. And it's basically a high-level view of a project that I've been working on over the last few months. Thank you very much for the nice introduction, Alessandro. Just to put a slide up about me, if any of you saw the name John Edwards and thought that I was the former US vice presidential candidate who got caught up in an extramarital affair, unfortunately, there won't be any salacious gossip on this talk today. We'll be talking about signal processing and AI. Signal processing, as Alessandro said, is something I've been involved with for a long time. And with the advent of IoT and artificial intelligence, applying signal processing to those applications is becoming more and more common and important. So before we start the actual talk, we're just going to take a break for a second because Amy has a little poll for you. And so it would be really interesting to find out if you could answer the questions. What level of digital signal processing knowledge do you all have? My screen has come up and said I'm not allowed to vote. Interesting results. So a third roughly have developed DSP algorithms in Python, MATLAB, or other high-level languages, and roughly a third have no DSP knowledge. But fortunately, there are some here who've developed some DSP algorithms in C and assembly, so they might be able to help out if I get stuck. So thank you very much. That's interesting. So for the guys who have a great deal of knowledge, forgive me, it's quite high level view, but I think given the answers, this is quite a good fit. To start with a kind of a little bit of a joke in the machine learning community, artificial intelligence is slideware and machine learning is software. AI is also obviously used for detecting cats v dogs on Facebook, which is fun, but it's not applying DSP to the real world, really. However, there is a serious point to this, and I'll refer you guys to the tech review from the MIT recently, which is more aimed at conferences and things. But it's interesting how the field of AI and the field of machine learning are evolving at such a crazy pace at the moment. My focus is really on machine learning, sometimes referred to the artificial intelligence of things. And the difference really between AI and ML is that in ML, we're using the cloud just as we would with more traditional AI systems, but we are learning in the cloud, training our models in the cloud, but then deploying at the edge. And actually, strictly speaking, the edge is a gray area in itself. In my case, really, we should refer to these edge devices as endpoint devices, because nowadays, if you have, for example, a home heating system, then there will be some level of intelligence in a server type device in your house, but the endpoints that are doing the temperature monitoring and so on are still quite unintelligent. So there's a difference really between the edge and the true endpoint. So what we're going to be looking at today is the endpoint. The nice thing I like about these types of machine learning applications is that the applications of these algorithms are vast and diverse. It could be home-based application, industrial machine monitoring, etc. It's a very diverse range of applications. But the key thing is that these techniques can be applied to, I believe, to many other more traditional AI and data science scenarios. So please bear that in mind as we go through the talk, that even though I'm going to be talking about the endpoint, I think these techniques, particularly with the frequency domain, have a much wider area of interest. So applications of machine learning, I've discussed a few. Image recognition is the big area. You know, self-driving cars is an area of great research and development at the moment. And these applications are super important, but they do require a very high level of processing capability in the device, in the car. But as I said earlier, there are potentially even more applications for applying machine learning to endpoints where typically the data is one-dimensional, streaming audio or vibration signals, and so on. So the types of applications where these techniques could be used are machine and vibration analysis, predicting failures of machines in the field. This is an area we'll look at in a bit, but other applications, speech recognition. I'm sure we're all familiar with the Google Home and the Alexa voice service. Medical healthcare, automatic patient monitoring is a very big growing area. Environmental monitoring. A colleague of mine has been involved in a citywide environmental monitoring application over the last few years. Health, safety and security, and of course, increasingly logistics and distribution. The thing is about these applications that they do not require the same level of MIPS, memory, power consumption, etc., as the more traditional AI applications, image recognition, and so on. So machine learning at the endpoint, as opposed to the edge, which I've kind of explained, has advantages over machine learning or AI in the cloud. And these are typically topics such as the latency. Having the machine learning at the endpoint gives a very, very low latency solution. There's cost benefits, particularly in communications. If this is a device working on a cellular network, then deploying the AI at the endpoint will significantly reduce the cost of the communications. Power consumption, again, if you can have a low power consumption solution at the endpoint, then that has benefits. And always on networks, again, if this is an application running on a cellular or a wireless network, then performing the machine learning at the endpoint can have big benefits. There is one other which I haven't mentioned here, which is security. If you can perform your operations at the edge, then clearly that's much higher security than communicating with the cloud. However, this deploying at the endpoint moves the cost function from the service provider to the consumer or the customer. Endpoints are clearly deployed in much higher quantities, and therefore cost is critical. And again, when I say cost, I'm talking about the whole system level cost, power consumption, the MIPS and memory requirements, etc., etc. So the question is, how can we help optimize machine learning recognizers for the above constraints? So let us look at an example application. And this is a diagram. In the top left, I've shown a spectrogram of a real application. It's actually a Rolls-Royce gas turbine engine. And the gas turbine engine from the point on the left of the graph is when the engine is turned on. And you can clearly tell from the graph that the gas turbine is being started up, and the audio's here. I won't play it, or we've all heard jet engines start up. So in this scenario where we have an engine that is changing speed, we actually want to remove the variation in speed from the sampled signal. And I won't go into the details, but the process of that is called an ordergram. And that's shown by the larger diagram on the right-hand side, where basically you can see, regardless, or I should say independently of the rotational speed of the engine, the orders are all placed in with constant separation. And that's kind of highlighted with an averaged order analysis graph, the red graph in the middle. So a couple of things that we can see from this, these diagrams is that the order analysis gives us very strong peaks and troughs, which we can try to detect. And, but that initial process of turning the spectrogram into an orderogram is, I'm sure, would be possible using AI algorithms, but I think it would be very difficult for an AI algorithm to learn that kind of process. So this is kind of an example of the kind of algorithm that is better implemented at the design process rather than just using AI to compensate. So looking at the Fourier transform in a bit more detail, and we'll excuse my spelling at the top there, the traditional AI model for analyzing signals and systems is to chuck a lot of data and MIPS and memory at the AI algorithm and let the algorithm do the work. So let's think about the frequency analysis at the moment, for a moment. Fortunately, a person by the username of Endolith, who I've no idea who this is, but should be congratulated for a really good piece of work. You can download the work from their GitHub. I've included the link here. And basically, they have developed a neural network that is trained to implement the fast Fourier transform. Now, initial thoughts as a signal processing engineer is this is awesome, because if we can teach AI how to do DSP, then that's great. I can deploy those algorithms and sit on a beach drinking pina coladas while the AI does my work. But unfortunately, if we look into it in a little bit more detail, we realize that using an AI algorithm to implement a fast Fourier transform requires a lot of MIPS and memory to infer the frequency domain output given a time domain input. So if we think back to the requirements of the gas turbine engine monitoring system, if we are trying to detect those peaks in the frequency domain, if we can convert the time domain series into the frequency domain, then we are making life a lot easier for the AI algorithm to recognize the features that will allow us to detect anomalies and so on. So Endolith has done some great work. If any of you guys are interested in maths and artificial intelligence, I'd strongly recommend that you clone the repo and just have a play with it, because it's a really fun piece of work that he or she has developed. So what we are going to do is we're going to use signal processing algorithms to perform a process called feature extraction, or sometimes referred to as feature engineering, to extract the features that highlight the characteristics that we are looking for in our signals. So thinking about the application, we have to train an AI model. And then once we have trained the AI model, we have to use that model to predict, in this case, for example, fault detection on the rotational engine. So when we take our time domain data in, we need to pre-process that data on both paths for the training data and the real-time analysis data. And we have to perform our front-end filtering, noise removal, level normalization, or orthogram transformations that we looked at before. Then we have to perform our feature engineering, spectrum analysis, Kepstrom analysis, peak detection, zero crossing detection, etc. And then only then can we pass the data, the pre-processed data, to either the training engine during development or the predicting engine at runtime. Once we pass if we're in a deployment scenario and we pass the pre-processed data to the predicting engine, then the final outputs from the prediction engine we will pass to a fault detection engine, which will look for the anomalies in the signal. So the majority of the talk today is going to be on this these pre-processing stages. And obviously it's important that we use the same pre-processing algorithms to train the model as we do at runtime for running the prediction on the sampled real-time data. So let's have a quick look at signal processing. And it's a very high level, very quick view, but here we go. So in our DSP system, we will traditionally or typically convert our signals from the analog domain to the digital domain for our signal processing. And then if we need to use our signals, for example, to control a machine, we will often need to convert from the digital to the analog domain for the real world control. So we're going to perform this transformation from the analog to the digital domain using a digital sampling solution, an A to D converter, which will convert our continuous time domain signal to our discrete time signal. And in the vast majority of applications, we would run our analog to digital converter at a constant sample rate, sampling frequency, which would give us constant time separation between successive samples in the digital domain. Now, it has to be said that's not always the case, and in rotational machines, sometimes it's quite common to vary the sampling rate, but in the vast majority of applications, we will have a constant time interval between our digital samples. And so this is all in the time domain. So how do we perform the processing in the frequency domain? Well, before we think about that, let's just think about a system, an analog system. And in this case, I've just shown a very simple analog filter, capacitor and a resistor, where we have a time constant. And we can replicate this analog system in the digital world using our digital filter. And you can see that the digital filter structure has a very similar structure to the analog filter. So the point of this slide is that we can essentially replicate any analog signal and system in the digital time domain. But it turns out that we can also represent any signal in the time domain. We can represent the same signal in the frequency domain. So here is a system response. It's actually a digital filter, but it could be any system. It could be a machine, a gas turbine. It could be any machine that we're analyzing. If we analyze the transfer function of that signal in the, the impulse response of that signal in the time domain, we can analyze the frequency response or the transfer function in the frequency domain. And not only can we analyze any signal or system, but we can also do the processing, which has benefits on our MIPS memory requirements during our processing. So the key thing is anything we can do in the time domain, we can also do in the frequency domain. But how do we convert from the time domain to the frequency domain? And the answer is that we use the discrete Fourier transform. The discrete Fourier transform is shown in the slide here. And at a high level, essentially, Fourier's transform says that we can take any real world signal in the time domain and represent it by a bunch of signals in the frequency domain, where each of those signals is a pure independent sinusoid. So we take our complex signal that we've sampled, for example, from our rotating machine. We separate out all of the components of that signal in the time domain into the separate components, sinusoidal components that compose that signal. And that is the Fourier transform. It is really just the separation of those signals. In actual fact, what we do at the end is we integrate the levels of each of those signals, those sinusoids, to give us the energies at each of those frequencies. And that's what we're going to look at in the next two slides. Just as a side note, arguably it was first developed by Gauss 17 years before Fourier published his paper, but that's just a side note that interests me. So let's look at what we all refer to these days as the Fourier transform. This is the equation for the Fourier transform. And don't worry if you look at this and just glaze over and you think, I don't understand this. There's way too many symbols here for me. The key thing is that this algorithm is really just a bank of filters. In the middle, we have xn multiplied by e to the minus j2 pi nk over n. Let's just simplify that for a second. All we're doing is multiplying our input sequence x of n by a bunch of filters where the coefficients are given by the exponential equation. And the complex exponential is just the sinusoids that are shown on the right-hand side in this slide. So essentially, Fourier's equation, the digital discrete Fourier transform equation that I've shown here, just says that Fourier's transform separates out all of those individual components given by the exponential function for every frequency k, and then sums the results. So that's where we have the sigma from n equals 0 to n minus 1, where big N is the length of the array. So all the Fourier transform is doing is saying, we're going to filter this signal, we're going to separate out all of the components that are the individual frequency components that we're interested in. We're going to sum the energies for each of those frequency components and then store those in an array. And that's how we get a graph such as the one on the right-hand side, where on the x-axis you can see all of the frequencies. This had a sample frequency of 500 Hertz, and you can see all of the frequencies shown on the x-axis, and the energies, which is the sum, shown on the y-axis, actually converted to dB, because dB is easier for us to visualize. So the Fourier transform, the discrete Fourier transform, is literally just a bank of filters converting our arbitrary input time domain sequence into a bank of energies for each of those filter frequencies. Now, I'm sure most of the people on this talk will be more familiar maybe with the term fast Fourier transform. The fast Fourier transform is just an optimization of the DFT. It works in exactly the same way. There are some limitations to the FFT, which we won't go into today, but the fast Fourier transform, for the purposes of this talk, is just an optimization of the discrete Fourier transform that makes it run an awful lot quicker. Okay, so we've had a high-level view of the Fourier transform. This next slide tries to show it graphically, where on the left-hand side we've got our input time domain sequence. We have a bunch of filters that are I've shown the coefficients for the filters in the middle, and then on the right-hand side we've got our frequency domain coefficients, which, if we remember from the previous slide, is just the sum of the energies at each frequency. So as the bullet points say, this is a lot of detail, and I'm sure for many of you that's maybe too much detail. But the key thing is this: the DFT is just a bank of filters looking at the energies at different frequencies, which is, if we think back to the application requirement of the vibration analysis, this is really exactly what we want. So let's return to our application and see how we can now use this information to assist. So this is, on the left-hand side, I show a block diagram of the entire process, from the analog to digital converter all the way through to the AI convolutional neural network, or the linear classifier. As well as the Fourier transform, we are performing some other operations, windowing. We won't look at these today, energy detection and conversion to dB. So there's quite a lot in this algorithm to get the data pre-processed before we can pass it to a linear classifier. And as a side, on the right-hand side, I've just given a quick summary of the deployment target that I've used for this development. And the reason I chose this device, it's an ARM embedded CPU. For those that are familiar with ARMs, it's based on an M33, a dual core 32-bit M33 solution. And the device also incorporates a DSP coprocessor. Now, clearly the DSP coprocessor that's built into this device is going to be very useful for all of the algorithms on the left, the Fourier Transform, the windowing, magnitude calculations, etc. But what we'll go on to look at now is the actual AI algorithm, and you'll see that at its very heart, the convolutional neural network is nothing more than a bank of digital filters. So this device is a very good target. So the ARM M33, and in particular this NXP variant, is a very good target device for these kind of algorithms. So let's get into the AI algorithm itself. And on the left-hand side, we see a traditional flow diagram of a neural network where we have a bunch of input samples. We have a hidden layer or a number of hidden layers, and then finally the output layer. This is as an algorithm typically referred to as a convolutional neural network. Multi-layer backpropagation, Perceptron, has various titles. But if we're thinking about the data flow, the signal processing, what I've highlighted in the flow diagram is that you see the paths from each of the, for example, from the input layer to the hidden layer, there are 3 banks of paths. One highlighted in blue, one highlighted in orange, and one highlighted in green. These are just traditional convolution signal processing operations. They're nothing clever, nothing special. They're just regular convolution operations. What happens in the nodes is the really clever bit. That's the AI bit. With the activation functions and all of the other clever AI-related operations. But the majority of the processing is just simple signal processing convolution operations. So that's great because that fits really well with the DSP accelerator in the target device that I used. So let's think about the vibration analysis example. The first thing we have to think about is the number of input samples, and that is actually the FFT length divided by 2. And in this case, we have 64 samples, and I can talk about why that is later. We're sampling at 16 kilohertz in this particular application, and we have 64 time domain samples. So on the left-hand side of our flow diagram, we don't just have the 4 samples shown here, we have 64. Then the hidden layer, we actually have 25, and I can talk about why I ended up with 25 later. And then the output layer, we have any number. It depends on the number of categories that we are trying to detect. Now, the benefits of the approach that I've used has ended up with a model size for categorizing these vibration modes of around 2 kilobytes model plus 500 bytes per additional output category. So that's about the size, very, very small model. The model accuracy is greater than 98%. And that is interesting because what I've found in my in my work is that the model accuracy is very dependent on the similarity between the two signals. Actually, there is an assumption there that we have a large amount of training data, but basically, if we have two signals that are, or multiple categories that we're trying to categorize that are very different, then the model accuracy is 100%. But as the signals become more similar, i.e. they have a higher cross correlation, then the model accuracy drops down a little bit to 99, 98%. In terms of the overall deployment power consumption, this application is running at under 18 milliwatts continuous power consumption. So very, very low power consumption. Because of the optimizations, which I'll talk about in a minute. So in summary, there's a lot to be gained from making AI intelligent AI. And I think intelligent AI is the way I like to think about this. It's not just taking a lot of numbers and throwing them at our AI system. It is thinking about the application, thinking about the type of data, the type of features that we're looking at, and engineering those features, and applying intelligent processing ahead of the neural network processing. Okay, so that's there's some additional information resources here if anyone is interested, and that's it for the presentation. Let's open the festival up to questions.
So thank you very much for your presentation. It was very, very interesting. So yeah, we've got some questions already. So I'll probably start from, why did you program the app in C and not use a standard API such as TensorFlow Lite?
That's a great question. So the driving function for this, for those that might not be familiar with TensorFlow Lite, I'm sure many people on this presentation will be familiar with TensorFlow. TensorFlow is one of the main APIs for developing AI algorithms. And there was a paper I read recently where it was comparing TensorFlow to some of the other AI APIs, and in industry, TensorFlow really is the primary API. There is an extension to TensorFlow which basically allows you to compress the models to run on really low power devices. And actually, one of the initiatives also promoted by Google is the TinyML initiative. I'd recommend everyone, if you're interested in this area, to look at TinyML. And I use that for some inspiration. The TinyML book is excellent. But back to answer the question, what I wanted to do was to be able to use the signal processing accelerators that are now available on these modern, very low power devices from ARM and other companies, XMOS, that I used to work with. So I wanted to target these accelerators, and very often these accelerators are just raw DSP engines. They're not targeted at AI, so they don't have the necessary APIs and so on. So I wrote this code in C to take, if you remember back to the slide where we looked at the AI algorithm and the stages and the convolution operation, to target those neural network convolution operations to the convolution accelerators that are on these low power processors. Now, as an aside to that, I could have trained the neural network using TensorFlow, And that was my original plan, and I did do that, and then just use the C code for deployment. But actually, if anybody's looked at the real low-level code of a neural network, once you have coded the inferencing engine of the predictor in C, actually converting that into the backpropagation network for learning is actually a relatively small piece of work. So having developed the low-level code to go on the processor for deployment, actually I then just modified that code for the learning and just did the whole lot in C. But I could have done it in TensorFlow, the learning.
Well, thank you very much for that, John. Just before we move on to the next question, I just want to remind everybody on the session that on the Q&A box you can upvote questions that you would like John to answer. So the next question comes from Simon. It goes, John, on the multi-layer backpropagation slide, why did you choose a hidden layer length of 25? Is that significant?
Good question. Yeah, so when I started this project, I wasn't, I didn't know how large the FFT should be, how large the hidden layer should be. I was really starting from scratch. There was very little literature out there in this application space. So what I started with on the input side, I started with an original FFT size of 512 points, which gave an input sequence length to the AI algorithm of 256 points. And so and my inner layer, again, I set very large so that I could be sure that that was not a limiting factor. And basically, I reduced the length of the input sequence down from 512 to 256 to 128 points. And at that point, it became a sort of law of diminishing returns, where the algorithm was no longer able to successfully characterize. So that's why I ended up with 64 input points. And then for the hidden layer, I did the same thing. I started with a very large hidden layer length. I think it was something like 256 or something like that. And as I reduced the number of input samples, I reduced that correspondingly. And then actually what I did for the final stage was I just wrote a script, actually a Python script, which was calling my C app. And I just ran it overnight, and I started with a small hidden layer size of 10, if I remember. And I just kept increasing it and storing the results in this, what turned out to be a very large log file overnight. And again, it was a law of diminishing returns. Once below 20 for the hidden layer length, it wasn't able to successfully detect the different vibration modes, but above 25, again, it was a law of diminishing returns. But interestingly, this comes back to one of the points I made in the slides, that answers to these questions really depend on how similar the vibration modes are that you're trying to detect. And the more similar they are, the more data points you need.
Thank you for that, John. Next question comes from Matko. Apologies for my pronunciation. So said, if we could quickly explain again why we should use the frequency domain instead of raw data.
Yeah, basically because it's all about the feature extraction or feature engineering. I believe quite strongly that the AI algorithms benefit when they are given really strong features to recognize. So the more we can do as data scientists and engineers to present the AI algorithm with strong features that are easily differentiable, then the better the results. Now, when I say better the results, actually, I probably should clarify that. I'm quite convinced that you could do all of this with huge amounts of data, huge amounts of learning, lots of MIPS and lots of memory. But there's a cost there. And that type of algorithm, if we just took the time domain data and chucked that time domain data at a very, very large AI algorithm, it wouldn't run on embedded processors. You'd need a much more expensive processor to run that kind of algorithm.
Thank you for that, John. And I suppose like a very similar question, did you do a comparison between using the time domain signal versus the frequency domain signal as inputs to your convolutional neural network classifier to see the benefit of transforming the signal into the frequency domain?
I didn't actually do that comparison. One comparison I did do was with the MEL frequency spectrum. And for those that are not familiar with it, the MEL frequency spectrum, or the MEL frequency Kestrel coefficients, is an algorithm typically used in speech recognition. So I don't know anything about, for example, Amazon's algorithm or Google's Hey Google algorithm, but I would be very, very surprised if at the front end of their speech recognition algorithm, they didn't perform some kind of MEL frequency Kestrel coefficient calculation. And the reason is they want to convert the time domain signal into the frequency domain exactly the same way as I have described here, because it makes it easier for the AI speech recognition algorithm. So I didn't actually do a comparison between time domain and frequency domain, because I think, you know, doing this frequency domain pre-processing is definitely the way to go. However, a valid question would be, why did I just use the raw fast Fourier transform rather than the MEL frequency spectrogram, or MFCCs as they're commonly referred to? And actually I did a comparison. It wasn't a scientific experiment. MFCCs is basically a way of reducing the number of frequency domain coefficients. That's all it is. It just reduces the number of frequency domain coefficients that you use in your AI algorithm. And I just got the feeling in the application I was developing that the linear spectrogram, the fast Fourier transform, was better because it gave a linear spectrum across the whole frequency range rather than the logarithmic MFCC spectrum of that algorithm. But I didn't do a complete scientific analysis of that, and it could well be that actually another alternative to the FFT would be the MFCC algorithm.
Thank you for that. And so a question from Alex. Given the number of pre-processing steps on a signal before we get to the ML network, can one measure how much modifying these steps would break the network's predictions? An example, modifying the humming window or sample frequency.
Yeah.
I'm curious from a software production risk perspective.
Absolutely, that's a great question, and that's where running Python scripts overnight on your computer is a really good idea. And again, I did a lot of this. So when I first developed the algorithm, I just wrote it using double precision floating point numbers in C, just using GCC, and so that's how I got the base model. And then actually, I didn't look, apart from varying the hyperparameters, so the number of input samples and the number of hidden layer points, I didn't do much there. But what I did do was look at the quantization of the convolutional neural network coefficients. And so I started with 64-bit double precision running on my laptop. And actually, I was able to compress them down to 32-bit and then 16-bit numbers. And again, it's a trade-off. So the numbers that I quoted in the presentation for the model size of 2 kilobytes plus 500 bytes per additional category were based on 16-bit coefficients. What I did find in that scenario was that actually I could reduce the quantization of the coefficients much more and get an even smaller model, but I found I had to increase the size of the input sample data set. Now, again, maybe that's a research topic for the future, like a lot of these questions that are being asked. I didn't do a proper scientific study and plot a graph. What I felt from my test was that 16-bit samples with the small input data set that I had were proved to be very robust. But as I say, you could play with all of these parameters. There are so many parameters that you could play with in this. It could be probably a research topic, a PhD research topic or something like that.
Thank you for that, John. And I've got a group of questions on the ordergram.
Yes.
So Adora is asking, is the ordergram output you presented earlier a type of fast Fourier transform computation, i.e. from spatial domain to frequency domain? And the related question, web search results for ordergram are sparse. Please may you recommend further reading, or is there an alternative term one might search for online?
Okay, so the ordergram is a form of spectrogram. The only difference is that the input data is resampled to adjust for the rotational speed of the engine. So basically, you can think about it very, very easily as the engine speeds up, we need to sample faster. So we could do that by varying the sampling frequency of the A to D, or we could set the sampling frequency of the A to D converter at the highest frequency we require, and then use software to compensate for the rotational speed of the engine. And that's exactly what I did, and that's exactly what I did with the ordergram. Actually, as regard references, I don't have them off the top of my head, but if anybody is interested in, has a question like that, feel free to email me or ask the question on the Data Science Festival website. I suppose the question for you or Amy, is there going to be a discussion page, web page where we could answer any questions like this? And then I can upload a load of references for people to look at.
I think we're going to take the questions that we are not able to fully answer here offline and probably follow up with an email.
Perfect, thank you.
So the next question comes from Phil. How did you get your labeled data?
How did I gain the labeled data? Yeah, so
yeah, how did you get your labeled data?
Yeah, I basically used, I might even have it here. So I have a calibrated microphone. I don't know if you can see it in the video. So this is a fully calibrated microphone and basically sampled a load of data from the required rotating machine.
Question from Ethan. So what would an alternative of classifying the same data using analog circuits look like? Feasible, less or more expensive in terms of hardware resources versus digital?
Using analog, that's an interesting question. Okay, so I have heard talk about analog variants of neural networks. And I can't really comment on that side of things. All my neural network work is digital. On the signal processing side, I can talk to that. Basically, the problem with analog signal processing is noise. Anytime you have a capacitor, resistor, op-amp, anything like that in a chain, you're going to be picking up noise. So the modern trend in signal processing, regardless of whether you do it analog or digital, the modern trend is to push the A to D converter as close to the transducer as you possibly can. And in fact, to that end, if you like, I mean, anybody on here that's involved in voice processing will probably be familiar with modern digital MEMS microphones, where the microphone itself, tiny little microphones measuring millimeters across, include the analog to digital converter in the microphone. So coming out of the microphone is a digital stream. So immediately you're processing digital data.
Thank you very much, John. And I think that's all the time we have for the questions. So we'll probably take any other questions that we haven't been able to answer offline for you, John, to follow up with an email. But again, thank you very much, John, for being with us today. A very interesting talk. And thank you all for joining us on this lunch and learn session. And I hope to see you all again next week. So yeah, thank you again and have a good day.
Thank you everyone for attending. I hope you found it useful as well. I've enjoyed it. Thank you very much, Alessandro, for hosting, and to Amy in the background for looking after us all. Goodbye.
Thank you. Bye-bye. Bye-bye.